Hi everybody, thank you for coming. Is everybody in good shape this morning? Yeah? Great. So let's talk about thousands lines of code I didn't write. So I'll introduce myself. My name is Valentin. I'm from Paris. I'm a member of the Scala community in France. I organize the Paris Scala user group, and I'm part of the team that organizes the Scala I/O conference. And before we begin, I have to warn you a little bit. I have only so much time and much to present. So there will be no time for cat pictures and funny things like that. There will be a lot of code that might look a little bit scary, but bear with me, it will be okay. And probably the code that I will show you isn't correct, but that's not a real problem. Okay, so this is the story of a project I've been working on in the past few years. And it was, we were a small team at a fairly large company in France that spans around 100 entities. And we were tasked to build a data platform that will collect and store all the data from the entities. Each entities have roughly 100 tables or streams or data structures. So it sums up to roughly 10,000 data structures. We started from scratch in June 2016, and we had to be on production by December of the same year. And we were a small team of 5 or 6 developers. So it's a data platform that data is coming through big batches, and we use Spark, or through streaming to Kafka topics. We had to implement so-called privacy by design, which means that the sources, the entities that gives us their data, are telling us which fields, which columns contain personal information, and we had to take measures to make sure that the privacy of the people was protected. And of course, it was a fairly big project, and we knew that all the data sources wouldn't give us their data on day one. They will come on the course of 1 or 2 years. So basically, when you, who is working with Spark? Okay. When you want to validate data with Spark, basically you write a Scala case class, and you use some kind of tooling to automatically validate some, say, a JSON document to make sure it complies to the structure of your case class. But we had 10,000 of data structures, so we wouldn't be able to have been able to write 10,000 case classes, right? We had only 6 months and 5 developers, so it's just impossible. So we understood that our pipeline would need to be configured at runtime. In other words, we wanted to have only a single artifact, a single piece of code, able to validate and transform all the data for all the sources. We needed a schema to that, and that schema needed to have a custom format, because we wanted the sources to be able to express that each field is or isn't a personal information. And of course, we had to work with multiple data formats, semi-structured in input, like JSON or CSV, and we wanted to transform it to more usable formats like Parquet or Avro. Right? Nothing fancy. So the solution we found was to build the whole pipeline around the concept of schema. We feed a schema into the validating process, and it builds up a validator that will validate then the incoming data. So that enables us to have a single piece of code that validates arbitrary kinds of data. And we had to take into account that specific schema with privacy concerns and so on. Schemas are cool. Actually, there are blueprints for building a whole bunch of applications. You can use a schema to build a validator. You can use a schema to generate random data. You can use a schema to translate data between different formats. So it was the good concept to build our pipeline around. And schemas are recursive structures. Inside a schema, you have smaller schemas that contain smaller schemas, and so on and so forth. And the data they represent, like JSON, for example, is also a recursive structure. Inside the JSON, you have smaller JSON objects, and so on and so forth. But the problem is that with recursive structures, you end up writing recursive functions. And there are various problems with recursive functions. Of course, it's difficult to make sure that your functions are stack safe. So you risk to have stack overflows, which is not really a problem with schemas and data because it's not deep enough to blow up the stack. But more importantly, when you write a recursive function, you are mixing two concerns. You are mixing how you walk through your recursive structure with what you are doing at each step, which means that your code isn't reusable, because if you have to write another function, you will again write how to walk through your structure and what you want to do at each step. This isn't cool. But in functional programming, we have a technique that's called recursion schemes that comes from a paper from 1991 with a very funny title, Functional Programming with Bananas, Lenses, Envelopes, and Barbed Wire from Eric Meyer. Was familiar with recursion schemes already? Okay, cool. And basically, recursion schemes are a way to decouple how we traverse a recursive structure from what we do with each element of that structure. And there is an implementation in Scala. The library is called Matryoshka. And it's a pretty much complete implementation. It's really cool. And so we decided to use recursion schemes to build all our process around schemas and data. So first, I will explain you a little bit about the theory, and then we'll see practical application of it. So recursion schemes define three families of traversals. First, you have folds, like in the standard library, the fold of a list. It takes a list, which is a complex object, and it destroys it, it collapses it to a single element. Who's already using fold in Scala? Yeah, cool. The most simple example of a fold is called kata. It's a katamorphism. It's like the same kata as in catastrophe, for example. Then you have unfolds. They do the converse. They take a simple element and they build up a complex structure out of it. There is a method called unfold in the Scala standard library, but it's more seldom used. And the simplest unfold is called ana, for anamorphism. And then you have refolds that combine a fold and an unfold. And the simplest refold is hylomorphism, like hylo. Oh, and one important thing to notice, we we will repeat that throughout the talk, is that folds, they destroy a structure bottom up. From the leaf, you fold the structure starting from the leaf. And unfold, they act top down. They start from the roots and they unfold until you have a full tree. It's important to keep that in the back of your mind. So, to use a recursion scheme, you need 3 elements. One is optional, but most of the time you need 3 elements. First, you need a functor. It will be called a pattern functor, and it's just a regular functor. You can do recursion scheme on option or list or thing like that, and it will be interesting. Then you need a fixed point. Who has already heard the name fixed points? Okay, cool. We'll see what it means and why it's useful. And finally, you need an algebra or a coalgebra or both. And these are the recipe of what you want to do at each step. Okay so far? Okay. So, let's start with a small example. First, we need a pattern functor. So, a typical recursive structure is the binary tree, right? So, usually, if we are to implement a binary tree in Scala, we will write a sealed family, like a trait tree and a node that has 2 branches, which are recursive trees, and leaves that only have a label or something like that. So the first thing we have to do is to change that type to replace each recursive occurrence with a type parameter, like so. Right? We also often add an f to the name of the type, so that we remember it's a functor. And so we have a node where each tree has been replaced by an A. Okay? And it's almost trivial to write a functor instance for that type. You just have to apply the function f to each branch of the node, and that's okay. Leaf is like nil for the list functor. It just contains nothing, so we just have to change its type parameter when we map it. Okay, so far so good. But there is a problem when we do that, because we become unable to have a single type for all our trees. Because now the depth of the tree appears in its type, right? Here I have a 2 levels deep tree, and its type is node of leaf of nothing. But if I have only a 1 level depth tree, its type will be node of leaf of nothing. And if I have mixed depth, an unbalanced tree, I have a even weirder type, right? So it's a problem because we want to write functions that takes trees, but we cannot find a type to label our trees. And that's when we need a fixed point. It's just a trick that hides or swallows the recursion in our structure. If we wrap each level of our tree inside this fixed case class, we get an uniform type for all our trees. So trust me, I have written again the trees from the previous slide using fix, which is not really practical, but it works. And let's work that out. Here I have a leaf. So if I fix this leaf, I have a fix of 3f. Okay? Again, if I have a leaf there and I fix it, I have also a fix of 3f. So this node here is a 3f of fix of 3f. And if I wrap it in fix, I have again a fix of 3f. Is that okay? And the same is with this more complicated tree, right? So it's just, you see the recursion here. We have f 2 times. So it just hides one recursive step, and it's enough to completely swallow the recursion at the type level.
Can we somehow get rid of the performance penalty for loop wrappers?
So the question is, does it imply a performance penalty, and can we get rid of it? Actually, there are multiple fixed point types. Fix is the simplest one. And wrapping always incurs a performance penalty. But for refolds, like hylomorphism, you don't need a fix. You only need a fix for kata and ana. So if you have a performance penalty, you first try to rewrite it using hylo rather than kata or ana. But yes, it's only a trick to please the compiler that incurs, of course, a performance penalty and more memory being used. So that's a good question. So we have a pattern factor, we have a fixed point type. Now we need algebras. So algebras is a big name just for functions. They define what we do with each layer of our structure, and are really, really simple. An algebra, it collapses one layer at a time of our function, of our structure, and it's simply a function from f of a to a. Right? You can think about high school algebra, where we were tasked to take big expressions and compute a result. The big expression is a f of a, and the result is an a. Okay? And like everything in category theory, when you add co in front of the name, you reverse the arrows and you get a new thing, and that's it. That is coalgebra. A coalgebra, it builds up one layer at a time of your structure, and it's just a function from a to f of a. And also, in the context of recursion schemes, the a of the algebra is often referred to as the carrier of the algebra. That's just a bit of vocabulary. So let's look at what it means and how hylomorphisms work. I choose to show hylomorphism because every other scheme can be implemented in terms of an hylo. So we need our pattern factor. It will be these little purple boxes. We need an algebra. We need a coalgebra. And we need two types, A and B. Here is the definition. It's fairly simple. It's the real definition from Matryoshka with a little rewriting there. And let's look at how it works. So we start with an A, right? Because we need an A to apply hylo on it. Then the first thing we have to do is to call the coalgebra on that A, right? And a coalgebra is just a function from A to FA, so it just produces an f of A. Since f is a functor, we can now map over it, and it's like picking inside its elements and applying a function. And the function we want to apply is hylo, because it's the recursion, right? And so again, we have to call our coalgebra on it, which produces an f of A. And so we can map over it, and again, call hylo, which calls the coalgebra and produce an f of A. But this time, I've decided it's a leaf, so there is no more element inside this f of A. So when I map over it, the function hylo isn't called, but it returns immediately an f of B. Okay, so far? So now that I have a f of B, I can call the algebra on it, and the algebra only takes an f of B to a B, so I end up with a B. And I finished for this branch. But before that, I was mapping over this node there. And maybe it has another element inside it. So I need to call either on it, which calls the coalgebra, producing an f of a, which is again empty because I decided it was a leaf. So when I map, the function is uncalled, and it returns an f of b, on which I can apply the algebra and obtain a b. Now I'm finished for the map of this node, and it has become an f of b, on which I can apply the algebra, gives me a b, and I'm finished with this branch, but I was still mapping over the root. Maybe there is another element inside it. I need to call ito, which calls the coalgebra. It gives me a leaf because it's becoming boring, right? Which is already an f of b. I call the algebra on it. Gives me a b. So now my root is only a f of b. I can call the algebra on it. And I have my b. And that's it. I have transformed an a to a b through a big data structure, which was a tree. And there are two important things to notice. Is that first, I only built one branch at a time. The whole tree was never displayed on screen, right? And I applied coalgebra while I was descending through the tree, and algebras while I was ascending toward the root. Is that okay? So you know everything there is to know about recursion schemes. Very good. So now let's apply this to our real problem. So we had a bunch of various schemas and data formats. We had our custom schema. We had Parquet, we had Avro, and we had probably many more. So the first thing we had to do was to define a pattern functor for the schema. And then we just defined a bunch of algebras and coalgebra to go from and to our pattern functor. And the first cool thing is that it gives us, for free, all these other hours. And this is really cool, because once you've written these little algebras, you're now able to transform a Parquet schema into an Avro schema, back and forth, which is cool. There is no library doing that. So let's look at what it means. I've simplified a bit our pattern functor, but this is the gist of it. We have structs that are only a map of string to field. We have arrays that only contains the type of its elements. And we have simple types, integers and strings and dates and so on. Again, writing a functor instance for that is pretty trivial. And we are good to go. Now we just have to write algebras to convert back and forth and forth. So for example, let's write an algebra that converts our schema F to Parquet schema. So in Spark, the name of the type families to describe Parquet schemas is data type. So this is a function from schema F of data type to data type. This is the very important point. The field here we get is the result of the algebra applied to the subtrees below. So it's already a Spark data type, right? So all we have to do is just wrap each field in a struct field, which is a Spark type, and then build a struct type, which is also the Spark's thing, to build a new data type. For arrays, it's even simpler. We have an LM, which is already a data type in the Spark world. So we just have to wrap it into array type. And for the simple types, it's even simpler. So this is really, really cool, because we only have to care about one layer at a time, and everything is already done for us. by the recursion. And to call it, suppose we have a fix of schema f, we just have to call the method kata on it with our algebra, and it gives us a data type. Okay? The other way around. Suppose I want to transform an Avro schema into my schema f. All I have to do is provide a coalgebra of schema f and schema, which is the Avro type for the schemas. So this is basically a function from Avro schema to schema f of Avro schema. Right? So again, I only have to build one layer at a time. I will build schema f that contains little smaller bits of Avro schemas. And it's pretty easy. Avro has this method getType, which tells me which kind of schema it is. If it's a record, I need to build a structf and just grab the fields and make a map of string to field. And again, this is an Avro schema. For the arrays, it's simpler. I just want to build an array f with the schema of the elements, and so on and so forth. Really easy. I don't have to think about it. It's really automatic. That's cool. I can transform an Avro schema into my schema f, but I have to tell the library which fixed point type I use, because there are many of them. And I can also automatically transform my Avro schema to pocket by using a hylomorphism, right? With the algebra I've defined just the slide before and the coalgebra. You find it cool? Yeah? Cool. So now I have played with schema enough. Let's validate data, because that's what we are tasked to do. So for that, we used the JTO validation library, which is the JSON and CSV validation library from the Play framework, but it's distributed as a single library. And it defines a type rule, which is basically a function that will take an input, like JSON or CSV, and produce an output or a list of validation errors. The problem with algebras is that you have to have a single carrier. So we needed to define a new ADT to represent data so that we could write algebras with a single output, right? So again, it's really simple. We called it data f. It's almost the same as the schema, but now arrays have lists of elements and not only the type of the elements. It's the only difference. And so producing a validator is really easy again. We start from a schema, and we produce a rule that will take JSON and build a fix of data f. Rule as an applicative instance, so we can use it to traverse a list, and it will give us a rule of list of fields. So we just, here we traverse the list with a function that takes a pair of the field name and the validator for the field, because again, we are in an algebra, so this is already a rule of GS value to fix data f. And we just use it. This is JTO stuff. And finally, we map the result to build a fix of data f. OK? That's the idea. That is important. How it works, it's not really important. You don't have to understand this thing. Again, for arrays, if we have a rule for elements, we can use the method picklist to make a rule for list of elements. And we use that to build a fix of GArray. And for simple types, it's even simpler. So that's it. We have a way to use schemas to build validators. We have a way to translate from one format to another. So we are almost done.
Where does the G come from?
Oh, it stands for generic. In that context, the problem with is that in Avro you have a type generic data, so we couldn't write generic data, and so that's why we just used the G. And since we already used structf, arrayf, and so on, it would have been confusing. Okay, so that was the simple stuff. So I hope it's still okay for you, because now we are getting into the more difficult stuff. I have 10 minutes? Yeah, okay. So we are going into the difficult stuff real quick. So everything isn't like easy as that. For example, with our schema representation, our schema F, we cannot directly build an algebra to produce Avro schemas, because the Avro API requires that every schema inside a schema, every subschema, has a single name. And we do not have enough information in our schema F ADT to come up with a name for each subschema. So we have to find a solution. There are actually two solutions. I might skip the second one for a moment, and we get back to it if we have time. But the simplest solution is to use the path of each schema element as the name of the Avro schema we are building. So in Matryoshka, we have a little, they call this utilities patterns. This one is called env, and it allows you to label each node of a recursive structure with a value of type E. So the idea is to start from the top with an anamorphism and label each element of the schema with its path inside the tree. So by doing that, we'll be sure that every node have a single name, and we can use that to build a Avro schema. So it's a bit noisy, but it's very simple. The only part that can come up into the path of a node is the name of the struct fields. So all we have to do, we start with a pair of string and fix of schema. And we build a label tree with the path. And we just use the path we already had. We put the name of the field at the end of the path, and we return an empty with that path and struct. And at the end, we end up with a root having path empty string, and then each of its fields have path, the name of the field, and so on, separated by dots. Okay? Okay. And so we just need to change a little bit our algebra to use that path. And since entity is a case class, we just have to pattern match on it. We have the path, we have the structs, and we can use, we need a namespace for Avro stuff. We can pass it to the algebra. And we just use the path to build a record, and then everything is just Avro stuff. We put the fields and so on.
So you would use with path to Avro catamorphism for Avro, and for the others you would use the plane without the end, right? Or not?
Yeah, you cannot, actually we wrapped all these functions inside a small library. And we explicitly say we want to transform this packet to Avro. So we knew that we needed the right algebra and coalgebra. Does that?
But does this pattern of using the entity, do I have to, once I start using it for Avro, do I have to use it for the other formats? Or,
oh, no. No, because you have one algebra per format. So The only thing that is common is the pattern functor. And everything around can move, and you can really do what you want. So we use that with simply pairing a schema with an empty path and calling hylomorphism with our algebra. I forgot to pass the namespace, I'm sorry. And the coalgebra that labels with the path. Okay? So I'll skip that for a moment. And now we have a last thing to do and it's to write our data that have been validated, so it's a fix of data f, to Parquet or Avro. So let's look at Parquet. In Parquet, when you use it with Spark, you just have to write a row and feed it to, I don't remember which method, along with the schema, and it will serialize it to the Parquet format. So this is convenient because we can nest rows inside one another. We are not forced to have linear rows. You can have structured columns. But in the case of simple types like integers, strings, and so on, we don't want to wrap them too much. So being able to wrap rows inside rows is cool because we can write an algebra. We have a unique carrier, a unique type. But we don't want each level to be wrapped in a row. Because, for example, if you have a 2 columns table, which we just want to output row of column 1, column 2, and not row of row column 1 and row column 2. So that's a problem because I said so far that we only care about one level of our structure, which means that we cannot know where we are in our tree when we are applying our algebra. So that's a problem, because basically we want to not wrap things inside rows when we are at the bottom of the tree. But there's a solution. There are another schemes than Kata, Ana, Ilo, and so on that have more sophisticated interface. And one of them is Para. It gives you what you've computed. So Para is a fold. So it's a descendant of Kata. It gives you what you've computed with the previous level, the subtrees. But it also gives you the subtree that you have previously destroyed. Okay? So for that, it uses another kind of algebra, which is called Geogebra. This is not the same G. It's for generalized. And it takes 3 type parameters, W, an F, and an A. And instead of transforming an F of A to A, it transforms an F of W of A to A. And that's used in Para to wrap the previous result inside a pair with the previous tree you have destroyed. So that looks like that. We build a GeoGebra that takes data F of pair of fixed data and row, and we produce a row. So here, if we imagine we have a function that tells us if a tree represents a simple type, like integer, string, date, and so on, we just have to check that the previous tree was a simple type. In that case, we had wrapped it in a row, but we shouldn't have. So we just need to unwrap it and build a bigger row out of these fields. And if not, we just use that to build a new row. Okay? And for simple types, we just wrap them, and they will be unwrapped one level above. So I think I'm running out of time. So I have many, many more usage I could have shown you, but I have only so much time. And I have a confession to make. Actually, I lied to you. This is inspired from real facts, but we didn't. Basically, we are refactoring our code using recursion schemes. We didn't start right out with recursion scheme. We wrote recursive function, and we suffered a lot, and we had many problems. But then we met with our mascot. Then we used Matryoshka, and it was really cool. And at first, when you start using that, you might feel like this poorly pixelated cat. It can look quite odd, but keep up, and it will get better. Trust me. Thank you.
Thank you.